Yeah. A very good evening from India. I'm Chandana BR, PhD scholar in the Department of Genetics and Plant Breeding from University of Agricultural Sciences, Bangalore. The crop on which I'm working for my PhD thesis research is our own crop from India, that is horse gram, which is said to be originated in Karnataka and Andhra Pradesh of India. For most predominantly self-pollinated crop like horse gram, pure lines are the only cultivar option. The recombinant inbred lines derived from bi or multi-parental crosses better than their parents or the existing cultivars serves as a new pure line cultivars. So to develop these recombinant inbred lines, a selection of good parents gives a head start to the breeding program. So the most important question in this scenario is how to select parents for making crosses. The quantitative genetic theory suggests that the probability of development of such transgressive RILs is maximum from crosses or breeding populations emanating from high mid-parental value. Therefore, breeders need to start with good parents. However, a good by good crosses might not result in exploitable genetic variants and transgressive segregation if the parents share same alleles. So without transgressive segregation, plant breeding would not work. So often plant breeders they tend to develop large number of crosses to generate genetic variation on which the selection is implemented. But not all the crosses that are developed are productive, and the resources we have are limited. So the selection and intensive handling of only a few promising crosses is the key to enhance the efficiency of plant breeding. So it is therefore necessary to select the best breeding populations from among those derived from good by good crosses. Therefore, breeders need to make selections at two different stages. One is that the selection of parents whose mid-parental value is higher for making crosses, and another one is at the selection of best breeding population. And the next question that comes here is, which is then the best breeding population? The best breeding populations are the ones with high predicted genetic gain, which we here refer to as usefulness index, which accounts for the mean, variance, and selection accuracy, and high transgressive segregation, and high predicted frequency of transgressive RILs. So in this presentation, I'll present my results on prediction of frequency of transgressive RILs and minimum population size required for their recovery in horse gram. And the hypothesis behind our study was the breeding populations derived from different crosses differ with respect to their mean, variance, and their combination, that is usefulness index and transgressive segregation. And the rationale of our hypothesis are the parents differ in the dispersion of number of favorable and unfavorable alleles controlling target traits, and the crosses also differ with respect to their mid-parental values. Hence, the breeding populations differ with respect to their predicted genetic gain, transgressive segregation index, and frequency of transgressive RILs. So with this preamble to predict the transgressive RILs, let me show how we developed breeding populations using these four genotypes, that is HPKM320, IC361290, PALM1, and CREDA18R, and these were differing in their growth habit. These two are of determinate growth habit type, and these two are of indeterminate types. And we crossed these four genotypes and developed two different crosses, that is HPKM320 by CREDA18R and IC361290 by PALM1. And the F1s were self to obtain F2s, and the F2s were further self to obtain F2 derived F3 population. And these F2s and F2 derived F3 populations were phenotyped for traits like primary branches per plant, pods per plant, pod weight per plant, and grain weight per plant. So for the prediction of probability of transgressive RILs, we need the estimates of mid-parental value and additive gene effects, which were estimated using multiple regression method using SPSS software. And we also need the estimates of additive genetic variants, um, which was calculated using the results of analysis of variance by subtracting the mean sum of squares due to error, by subtracting the mean sum of squares between F2 derived F3 families and dividing it by number of replications. And assuming that the data follow normal distribution, the probability of recovering the RILs that are likely to transgress the better parent and two check varieties, namely PHG9 and BGM1 that we used for our study, was estimated as standard normal distribution integrals corresponding to the values of additive genetic effects. Uh, uh, Additive genetic effects by standard deviation of additive genetic variance, and the RILs that are likely to transgress the check varieties were calculated as mean of check variety minus mid-parental value by standard deviation of additive genetic effects. And the minimum population size required to recover the RILs that transgress the predetermined standards was predicted as the n is equals to log of 0.05 by log of 1 minus p, where p is the probability of RILs that transgress the predetermined standards, and 1 minus p is the probability of RILs that do not transgress the predetermined limits. So coming to the results, the predicted frequency of RILs that transgress the better parent for primary branches per plant was higher in HPKM 320 by CRIDA 18R, whereas the predicted frequency of RILs that transgress the better parent for pods per plant, pod weight per plant, and grain weight per plant was higher in the second cross, that is IC361290 by Palem1, than the other cross. Therefore, lesser the minimum population size required to recover those transgressive RILs. And the same trend was observed where same cross IC361290 by Palem1 showed higher predicted frequency of RILs that transgress both the check varieties, that is PHG9 and BGM1 that we used for our study, for the traits like pods per plant, pod weight per plant, and pod and grain weight per plant. And therefore the lesser the minimum population size required to recover those transgressive RILs. Here you can see the predicted probability of RILs that transgress the check variety BGM1 also followed the same trend, where this IC361290 by Palem1 cross showed better performing RILs. So this emphasizes that the extent of dispersion of additive effect alleles that induce more pods per plant, pod weight per plant, and grain weight per plant is higher between the parents IC361290 by Palem1 cross than between the HPKM 320 by CRIDA 18R cross. So based on these results, IC361290 by Palem1 cross showed to have a better breeding potential in terms of greater predicted frequency of transgressive RILs and lesser minimum population size required for their recovery. So with this, we believe that this method of assessing the breeding potential of crosses at early segregating generations based on predicted probability of transgressive RILs that could be derived in advanced breeding populations and predicted minimum population size required to recover them, it sounds practical for a breeder. So therefore, early elimination of poor crosses based on this objective criterion allows the increased allocation of resources only to a few promising crosses for identifying the superior RILs for them to use as a pure line cultivars in self-pollinated crops. Finally, I would like to acknowledge my chairperson, Dr. Yas Ramesh, for his scientific advice, constant supervision, and vivid encouragement. I'm grateful to the Department of Science and Technology, Government of India, for providing me financial assistance in the form of fellowship for my research. And I'm grateful to the University of Agricultural Sciences, Bangalore, for providing the great platform to study, learn, and conduct research. And I'm also grateful to the Dalhousie University Global Research Program for providing us this platform to present our work. Thank you.